So good evening, students. Good evening. Right. We'll get started. Right. So yesterday, what were the concepts that we were discussing? We saw some important concepts. One is coefficient of viscosity. So those who are online, you're able to hear me, right?
Yes, sir.
Right. So we saw something called as coefficient of viscosity. Then we saw some problems based on that, right? What were they? So what was the formula that related viscous force with coefficient of viscosity? Neta into A into dV divided by dx. So neta is the coefficient of viscosity, F is the viscous force, A is what? The area of the liquid which is in contact with. Then dV by dx is called as velocity gradient. Right? We called all those things. Next. So we solved some problems also. Then I explained about the Stokes law also. What does Stokes law mainly speak about? When a solid is moving inside a viscous liquid, what will happen to it? So there was a theory that we discussed. Right before we discussed Stokes law, there is a theory that we discussed with what happens when an object, a solid object, is dropped into a viscous liquid, right? So when a solid object is dropped into the viscous liquid, what happened? So the layers of the liquid which were in contact with the solid. So first point, what happened? The layers which were in contact, the layers of the liquid which were in contact with the solid started moving with the same velocity as that of the object. But whereas the layers which are far away, they were at rest, right? So due to this, what happened? There was a relative velocity appearing between different layers of the liquid in the vertical direction, due to which, what can you say? There is a viscous force which acts tangential to the object, right? Tangential to the object, and the viscous force will keep increasing as it moves in the downward direction, and at one point it will become a constant. And when it becomes a constant, the velocity attained by that object is what we call it as terminal velocity, right? So now what is Stokes law? See, the concept which we discussed about the ball dropped into a viscous liquid is the theory involved in what happens behind the motion of that solid. Okay. Now what does Stokes law mainly speak about? It speaks about the viscous force experienced by a small spherical surface, right? So according to Stokes law, what happens? The backward viscous force which is acting on a small spherical body of radius r moving with uniform velocity v through a liquid is given by what equation? F is equal to 6 pi into neta into r into v, where neta stands for coefficient of viscosity, r is the radius of the spherical ball, and v is the uniform velocity that is attained by the ball after it travels a certain distance. Right? I hope everyone is clear, right, with this?
Yes, sir.
Right. So we'll see what is the derivation of Stokes law. Okay. So the viscous force that we spoke about, shall I proceed? Yeah. So the viscous force that we spoke about was observed to be dependent on three important attributes or three important parameters. What were they? One is the radius of the spherical ball, one is the coefficient of viscosity, and the last one is velocity. So when I take all these parameters into consideration, can I say that F is directly proportional to neta power A, V power B, and what is the other parameter? R power C. You're able to understand what I told? Let's repeat it. So derivation of Stokes law, the viscous force then acting on a sphere moving through a fluid may be dependent on what parameters? Coefficient of viscosity, radius of the spherical body, and velocity. The uniform velocity, right? So what method am I using to derive it? This is called something which we discussed in the second chapter. Some analysis. We call it as dimensional analysis. Right? So what should we do in the next step? F is equal to K into neta power A, B power B, and R power C. Okay. So what should happen next? Dimensional formula of F should be equal to the dimensional formula of neta raised to the power A, dimensional formula of B raised to the power B, dimensional formula of R raised to the power C. Correct? So what is the dimensional formula of F? M L T minus 2 is equal to the dimensional formula of beta. Look at your notes and tell me. ML T minus 1. So ML minus 1 T minus 1, the whole power A. What is the value of B? L T minus 1 to the power B. And what is the value of R? L power C. Okay. So MLT minus 2 is equal to M power A, L power minus A plus B plus C. Accepted? Into T power minus A minus B. So what should we do next? Why didn't I take the value of K into consideration? So it is a constant without dimension. It is a dimensional response. Okay, so whenever you are doing dimensional analysis, you should always introduce a constant which does not have any dimensions. So comparing both the sides, A will be equal to 1, minus A plus B plus C will be equal to 1. And what about minus A minus B? What is minus A minus B?
Minus 2.
Minus
2.
Correct. So it is minus 2. So if I take all these values and try to solve, if I put A is equal to 1 in this expression, minus 1 minus B is minus 2. So B is equal to 1. So A is equal to 1 and B is equal to 1 if I substitute it here. Minus 1 plus C is equal to 1. So how much is C? C is also equal to 1. So A, B and C is 1. We know that F is equal to K times neta power A, R power, V power B and R power C, which implies F is equal to K times neta R V. Right. Experimentally, it was observed that the value of K is equal to how much? 6 pi. So experimentally, K is equal to 6 pi. If I substitute it here, then the value of F comes out to be 6 pi neta R into V. Okay, 6 pi neta R into. Alright. So this is what we call it as Stokes Law. Can you put on the mask? I didn't combine. Where here? Minus A plus B plus here. Because here it is L power minus A into that is for the definition. That I told you, right? If you have to define something, you need to bring a relation between the quantity on the right hand side and the dependent variable on the left hand side. That is why we made the other values as one. That was not dimensional analysis. That was substitution of unit value. Whereas here, what are we doing? We are deriving the relation between all the physical quantities on which force is dependent on using the dimensional analysis. That is not dimensional analysis. So this is what you're asking. F is equal to neta into A into dV by dx. Right, here I put A is equal to 1 and dV by dx is equal to 1. Then what will I get? I will get F is equal to neta numerically. I was trying to define it. Whereas here, what am I trying to do? You are finding the relation between them. Okay, there is a difference. That is experimental here. You need not worry about it. Okay. So this is for what? This is only for viscous force acting on a sphere, not for all the objects. If had you dropped a cube, this would have not been the relation. There is a viscous force experienced only by spherical object. Okay, that too, its radius will be slightly small. So what are the conditions under which Stokes law is applicable or valid? Let's see what it is. First, the fluid through which the object moves has infinite extension. Okay. Secondly, see, these are all again not for the exam point of view, these are only for your knowledge. Okay. So the fluid through which the object moves has infinite extension. Secondly, the object is perfectly rigid and smooth. The object is the solid sphere they're trying to talk about. Third, there is no slip between the body and the fluid. Okay, it is only there is no slip, then the object can move with the constant velocity. Fourth, the motion of the object does not give rise to turbulent motion and eddies. So it should move steadily. Hence, the motion is streamlined. Last, the size of the object is small, but it is larger than the distance between the molecules in the liquid. So if you take the distance between two consecutive molecules in the liquid, the size of the ball should be comparatively of greater value, but on a whole, it should be of a small value. So it's a small sphere that you take into consideration. Where is the object considered to be rest? It is something like this only, slow and steady. Means they're trying to say that the object is supposed to move slow and steadily, it should not move fast. That is the meaning. So streamline doesn't mean every part is moving with the same velocity, not that case. So what does streamline tell you? If at all you take a particular layer, if an object is reaching on that particular layer at that point, then that should have the same velocity. It is not necessary that this layer and the upper layer should have the same velocity. That's not what they do. They're able to understand. So that is what happens. Right. Again, as I told you, I'll be sharing these notes. This part is only for knowledge. I'll write it here if you need. Only for knowledge purpose, not from exam point of view. Okay. So having all these points in mind, the last concept that is related to, actually the last but one concept that is related to viscosity concept is terminal velocity. Okay. So let us look at it like a question. Okay, terminal velocity is basically represented with the symbol V with a suffix T, capital T. Okay. Explain, so let us look at it like a question. Explain how does a body attain a terminal velocity when it is brought from rest at a viscous medium first. Second part is derive an expression for the terminal velocity of a small spherical body falling through a viscous medium. Also discuss the result. Okay, as I told you, this is the one which you will be doing in your lab as an experiment also. At that point, you better if you know the theory behind why you're doing it. Okay. So let us first, so what is the first part they are expecting us to know? Explain how does a body attain a terminal velocity when it is dropped from rest into a viscous medium. It is the same explanation that we saw here. Viscous drag is there, no? So when a body falls through a viscous fluid, what will happen? It produces a relative motion between the layers, accepted? Because the solid will be in contact with the liquid, moving with the same velocity, the farther layers will be at rest. So there is a relative velocity. As a result, the body experiences viscous force, which tends to do what? Retard its motion. So had the viscous force not existed, what would have happened? the object would have continued to move under the influence of its own weight. Right? It would have started moving, but there is something to oppose it. Who is there? That is a viscous drag. As a result, what will happen? Okay, which tends to retard the motion. As the velocity of the body increases, so it is still trying to accelerate in the downward direction. Though the retarding force is there, it is still accelerating. Why? Because of its own weight only. Right? As the velocity of the body increases, the viscous force that is coming to picture will also increase. Means what will it try to do when it is trying to accelerate in this direction? This will try to increase its force in the opposite direction. Its objective is to stop only, right? It will increase, right? So the viscous force, which viscous force? It is 6 pi eta r into v that we derived now, is going to constantly increase. Then after all this process is over, there will be a particular stage where the object starts moving with the uniform velocity. At that point, what are all the parameters that are getting balanced? So weight of the object is in downward direction. So the viscous force is acting in the upward direction, but at which point? At tangential point. Correct? At tangential point. But the other parts of the solid, suppose this is the solid, okay? I'm taking the bottom part of the sphere. Its weight will be acting at the center. Viscous force will be acting at the tangential parts. Then, due to this weight, what is the other force that will come into picture due to liquid? Liquid has another property also, right? It will try to push the solid outside due to buoyancy. So, the liquid will experience. So, weight is due to the solid. Due to liquid, there are two forces. What are they? One is the buoyant force, which acts through the center of gravity itself, and one is the viscous force, which acts at the tangential point. Now, all these forces are supposed to get balanced for this kind of a dynamic equilibrium to be attained. You know what is dynamic equilibrium, right? What is it? When the object does not accelerate, but still moves with uniform velocity. Right? So this is what happens. So a stage is reached where the weight of the body equals to the sum of the upthrust and the viscous force. So then what we can conclude, then there is no net force that is acting on the body and it starts moving with a constant velocity. And that constant velocity is what we technically call it as terminal velocity. Are we clear? Right? So now let's define it. So what is happening? Is it it will not rotate? No, that's what is mentioned. Stokes law is valid only when the object does not create any turbulent or radius. It should not rotate. If it rotates, Stokes law, what did I say? For knowledge purposes, Stokes law, what is the fourth point? The motion of an object does not give rise to the turbulent or radius. If it rotates, then angular momentum is generated. It should not happen. Then this whole law will fail. So that is why you need to ensure while the experiment is done also, you need to use the viscous liquid in such a way that the object should travel as slow as possible. But it should travel. As slow as possible. Then you will get accurate results. Okay. Now we need to answer a question. Now our job is to, we understood how terminal velocity is generated. Now our job is to understand how to define it. If I have to explain the same thing as a definition to someone else, how am I going to do it? So the theory tells me that the object is accelerating. So when it is accelerating, the object's velocity is increasing. So when it is increasing, after increasing to a maximum value, what would have happened? This velocity would have come into picture. So that is why the definition of terminal velocity should start with the word, the maximum velocity. Look at the definition. The maximum velocity acquired by an object under what scenario? While falling through a viscous medium. What we call it as terminal velocity. Whatever it is, but the logic is still the same, right? Okay, so you're talking about the buoyant force, you try to push it upwards. That is completely subjective. Like you're talking about a completely subjective case where you're taking a specific case into consideration. Maybe for that case, this thing is not valid. That is why I told you when you're doing the experiment, you need to have all these parameters in your consideration. So theoretically, you're saying something like this is going to happen. The liquids will also be chosen later. For example, we know this fact, right? The law of flotation says something like this. When a When an object of lower density is dropped into a liquid, what will happen? It will start floating, right? When a solid of equal density is there with respect to liquid, what will happen? In the midway, it will be at equilibrium. What if the density is
Partial
greater?
fold.
If you go and sit at the bottom. So there you are not taking the viscous force into consideration. So when you're stating Archimedes principle, what are you saying? You're only taking upthrust into consideration. Why are you not bringing the viscous force into consideration? It's not about you're not concerned. Why if the liquid has viscosity? If the same experiment is done in castor oil, it is viscous liquid. But why are we not speaking about it? Because there the object is not moving. Viscosity comes into picture only when there is a what? Relative velocity existing between the layers. Please have this in your mind. Relative velocity means the object is in motion. Okay. So your question of mass, density, and everything is subjective to that particular scenario of what materials you are considering. Are you able to understand what I'm trying to say? So I cannot answer that question. That is what I'm trying to say. Right. I hope you understand what I meant by subjective. It depends on that particular scenario. Right. So this is a general case what we are trying to say. So is there any doubt, guys? We saw the theoretical part. We understood how the terminal velocity is generated. Right. Now the next job is to derive that expression. So how do we do that? So write down expression for terminal velocity. This is an important derivation. Please write it down. So you are considering a spherical body of radius r. That's what we are doing, which is falling through a viscous liquid of density sigma. So this is another symbol for sigma. So you would have seen the sigma, right? This is generally used for summation. So both are sigma only, like how we have small a and capital A. There are two different cases. So sigma, and also this is the density they're trying to talk about. Okay, sigma and the coefficient of viscosity meter. Then we need to define the density of the solid. That's all. That is all I'm going to tell. After that, I'm going to show you how the derivation is. So what are all the parameters we have considered? So consider a spherical ball of radius r, density sigma, right? So which density have they taken as sigma? Viscous liquid density is taken as sigma. So the density of the substance, let me call it as rho. And sigma is what? It is the density of liquid. Then what else is there? Coefficient of viscosity. No. Are we ready to see the derivation? Shall we start? Okay. Tell me how the free body diagram is going to look like. One is the weight of the object will act in the downward direction. So what is the weight? Density of the solid into volume of the solid into g. Mass into acceleration, mg. Right. So what will be the tangential force that will be acting? Will be 6 pi neta r into v. Accepted? 6 pi neta r into v. Then what is the buoyant force that will act? What is the buoyant force that is going to act? Buoyant forces, I told you already, what does Archimedes principle state? Weight of the liquid displaced. So weight of the liquid displaced is density of the liquid into volume of immersed portion of the solid. So here the solid is completely inside the sphere. So can I write it as volume of solid into G? Is anyone having any doubt in this? Is it clear? Right. So what will be the relation between all these parameters? Rho into Vs into G is the only downward force is balanced by sigma into Vs into G plus 6 pi neta Rv. But what is the solid that you have considered here? It's a sphere. What is the volume of the sphere when you know its radius? 4 by 3 pi r cube. So rho into 4 by 3 pi r cube into G is equal to density of the liquid is sigma into volume of the solid is still 4 by 3 pi r cube into G plus 6 pi neta r into V. Am I clear with this? Right. What is our job? We need to find this V. I'll call it as Vt. Terminal velocity. So I'll leave 6 pi neta r into Vt on the right hand side is equal to 4 by 3 pi r cube into G into rho minus sigma. Tell me if there is any doubt. I took this whole expression to the left hand side. That's it. Then I swapped and wrote. I hope it's clear, right? So what will get cancelled? R and this will get cancelled. So this goes 2 times and this goes 3 times, and pi is also cancelled. So Bt will be equal to 2 divided by 9 into R square multiplied with rho minus sigma into G, the whole divided by neta. So this is the expression for terminal velocity. So in the lab, if you see, all these parameters are easy for you to calculate, is it not? So generally, when you derive a formula, it should be in such a way that this formula should be supportable in the lab as well. So 2 by 9 is a constant. Density of solid and density of liquid you can find from these specifications. G is known to us. Neta will be given to us because it is also there in the specification. So R you can find it out. Using vernier caliper, you can find out what is the value of R. So this is how it looks. This is the value of terminal velocity.
Yes, so like for buoyant force, why are we taking the volume of solid instead of volume of liquid displaced?
Volume of, see, weight of the liquid displaced is equal to the weight of the immersed portion of the solid. That is what Archimedes principle states. Right? Suppose there is like this. Okay. This is the immersed portion of the solid. Right? Let me say the volume of this immersed portion is Vi. Then upthrust, the buoyant force is equal to, okay, generally upthrust is written as F with the suffix B. What is it? It is the density of the liquid that is displaced. How much density of the liquid will get displaced? Sorry, how much volume of the liquid will get displaced? It is how much our volume you have immersed
Yes.
into G. Now in this case, the volume of the immersed portion is equal to the complete solid. That is why I took the whole solid.
Yes.
Yeah. So this is how you calculate terminal velocity. I told you about the Poisson equation. I can't explain it now because I have to explain about capillary action and all those things, which is the next part. I need to explain about surface tension that we can see later. But as of now, with the current knowledge that we have, we'll try to solve some problems based on this concept. Shall we proceed? So there are some important observations that you can. So let's see what they are. Let me read them out. This is also for your knowledge. See, Figure 10.27 shows how the velocity of a small sphere dropped from rest. So there is a, what is rho? It is the density of the solid. Okay. So if you draw a sphere, initially when I say drop, what is going to be its velocity? 0. So the velocity is 0 when the time is 0. So after that, what is happening? The object is accelerating. Right? It is accelerating, and its velocity is increasing in this way. Right? Then what is going to happen? After a certain time, you can observe that the velocity becomes a constant, and that constant velocity is what we call it as terminal velocity. Are you able to see that? Is it clear? I'm not able to see it. So velocity is on the y-axis, time is on the x-axis. Is this graph clear for you? Right, that is what they're trying to say. Figure 10.27 shows how the velocity of a small sphere dropped from rest into a viscous liquid medium varies with time. Initially, the body is accelerated, and after some time, it acquires constant velocity. So the velocity will increase in this way, and it attains a constant value. Secondly, the terminal velocity is observed to be directly proportional to, so look at the expression, 2 by 9 into r square into rho minus sigma into g divided by meter. So velocity is directly proportional to whom? The square of the radius of the object. So that is why they are taking an example. If you take bigger raindrops, they fall with larger velocity compared to the smaller raindrops. So they'll have greater terminal velocity. That's what it says. Secondly, the terminal velocity is directly proportional to what? The difference in the density of the solid and the liquid, sigma minus rho. Right? So if sigma is greater than rho, what is the meaning of it? Sigma is greater than rho means the solid is more denser compared to the, did I say sigma minus rho? Sorry, rho minus sigma. So if rho is greater than sigma, what will happen? That is, the density of the solid is greater than the density of liquid. What will happen? The body will attain terminal velocity in the downward direction, because obviously it will move in the downward direction due to its own weight. That's what the law of flotation also tells us. Secondly, if rho is less than sigma, what will happen? If rho is less than sigma, the object tends to float in the upward direction. As a result of this, what will happen? The body will race through the fluid. That is why, so see, the terminal velocity in this case will be negative, because rho minus sigma will give you a negative value. So what will happen? The body will start moving in the upward direction. That is why they are giving an example. That is why air bubbles in liquid and clouds in sky are seen to move in the upward direction. There is a reason why it is happening. Yes. So the air bubble and all, you will learn it under surface tension. That point you will get clarity why it is spherical and all those things. Okay. And what will happen if rho is equal to sigma? I asked you this. So the object will get suspended somewhere in between. It will either move in the downward direction or in the upward direction. It will float somewhere in the middle. So it is indirectly covering the Archimedes principle also. Are you able to understand? Next. The last one is, it is inversely proportional to something. It is inversely proportional to the viscosity, the coefficient of viscosity of the liquid. So the more is the more viscous the fluid, the smaller will be the terminal velocity attained by the solid. Okay. Next, what are all the independent parameters? So if you take a bigger cube and you drop, how much ever distance it is traveling, it is the terminal velocity is going to be independent of it. That's what they're saying. The terminal velocity is independent of the height through which the object is dropped. Okay. Last. So knowing the values of rho, sigma, r, and b, we can determine the. So there's the. So sometimes if you want to find the coefficient of viscosity, okay, if you want to find the coefficient of viscosity, that time what you can do, you can do the experiment to find the terminal velocity and then substitute it in this formula that will give you the coefficient of viscosity. So this is how you experimentally find out the value. Are you able to understand? So now, having all these concepts in mind, we are going to solve some problems. Think before you solve. Don't apply the formula. Think if you are able to understand the logic and do it. So example 42. There is a raindrop of radius 0.3 millimeter. So there is a raindrop of radius 0.3 millimeter which falls through air with a terminal velocity of 1 meter per second. The viscosity of air is, are you able to see? Clear, right? Okay. So a raindrop of radius 0.3 mm falls through air with a terminal velocity of 1 meter per second. The viscosity of air is found to be 18 into 10 power minus 3 poise. Poise is CGS or SI unit? It's a CGS unit. And all other things, it's a mixed combination. Now your job is to find the viscous force on the raindrop. So generally if you take the raindrop, it is assumed to be what shape? Spherical shape, right? So for the sphere, the radius is given. How much is it? Please write it. 0.3 millimeter. R is equal to 18 into 10 power minus 3 points. Minus 3. Sorry, minus 5. Sorry. Minus 5. 18 into 10 power minus 5 points. So how to find the viscous force? F is equal to 6 pi neta R into V. That's it. Do it fast. 6 pi neta is 18 into 10 power minus 5. So what is the relation between poise and decapoise? 1 decapoise is 10 times poise. So 1 decapoise will be equal to how many poise? 1 by 10. No? So reverse. No?
Sir, 0.3 millimeter will be equal to 0.3
minus
into 10.
3.
Sir, in centimeter?
0.10 power minus 2. Centi is 2, milli is minus 3.
Yes, sir. So, like in the solution, they have given wrong, I think.
Where
Sir,
0.03, check. You want in centimeter, they have written it in terms of, okay, we can write in terms of this one. So 0.3 millimeter, 0.3 into 10 power minus 3 meter. So 0.03 into 10 power minus 2 meter, accepted? 10 power minus 2 meter is centimeter, so 0.03 centimeter, correct?
okay, fine.
So it's better you solve it in CGS unit itself. That is easier. You can write the answer in terms of dynos. Huh? Okay, calculation part is not right. You understood the concept, right? So we'll go to the next problem. So look at the next problem. What are they trying to say? There is an iron ball of radius 0.3 centimeter falls through a column of oil of density 0.94 gram per cc. Okay, write down the values. What is the radius of the iron ball? So write down. So whenever you are reading a question, don't read it complete. Okay, there is an iron ball of radius 0.3 centimeter which falls through a column of oil of density 0.94 gram per cc. So if I read the question right, I'll understand two things. So when they say about iron ball, what comes to your mind? It's a solid. When they talk about oil, It's a liquid, right? So I don't even know whether they're trying to talk about Archimedes principle or anything. I'm not concerned. But I understood that there is a concept of solid in contact with a liquid. Now I'll start reading the next point. It is found to attain terminal velocity. Now I understood it is based on viscosity, right? So it is found to attain a terminal velocity of how much? 0.5 centimeter per second. So Vt is equal to 0.5 centimeter per second. Determine the viscosity of oil. I told you neta is equal to, you have a formula, provided you know the density of iron to be 7.8 gram per centimeter. You know the formula, apply it fast and get the answer. So what is Vt equal to? 2 by 9 r square rho minus sigma into g divided by neta. Take neta to the other side, bring Vt to the right hand side. So everything is in which unit? Which system of unit? CJ. So you can read the answer in terms of Poissons. Good first. Only thing is when you are applying, when you are doing everything in CJ's unit, take the value of G as 980 centimeter per second square. Got it? Huh? It is 980 centimeter per second square. Okay, you understood the concept? Leave some space for calculation. The answer that is given is 268.9 points. You got the answer? Okay, leave some space, you can do it later. Okay, let's do some more problems. Shall I move on to the next one? We'll have some interesting problems. By the way, guys, with this viscosity concept is over. There is nothing else to discuss. Okay. So I think that was the last topic which I gave for today's schedule, right? I'm not sure if you guys have checked it. That is the thing. So with what is it? Because everything is the serious only, right? If you write G also as 980, why is the serious unit only? That is serious unit. So when you're solving the problem, you're finding neta. This expression will take care of the units. You need not worry about it. You will have gram second per centimeter square, gram per centimeter per second. There are two units. One is a dyne second per centimeter square. 9 second only, no? 9 second per centimeter square. One is gram per centimeter per second. Shall we try the next one? With what terminal velocity? With what terminal velocity will an air bubble of density 1 kilogram per meter cube? Write it down. Air bubble of density 1 kilogram per meter cube. So when they say air bubble, sphere is running in my mind. Okay, of density 1 kilogram per meter cube and 0.8 millimeter in diameter. So what is the radius? 0.4 millimeter. Okay, rise in a liquid of viscosity 0.15 Newton second per meter square. So I repeat the question: with what terminal velocity will an air bubble of density 1 kilogram per meter cube and 0.8 millimeter in diameter, they themselves told, rise in a liquid of viscosity 0.15 Newton second per meter square and specific gravity 0.9. When can the object rise inside the liquid? When the density of the solid less than that of the density, right? That is what is going to happen. So 1 minute. Did they give the density of the liquid? Specific gravity is given, right? So with specific gravity you can find it out. Specific gravity is what? relative density. Specific gravity is relative density. Okay. So what are all the data given? With what terminal velocity will an air bubble of density 1 kilogram per meter cube? So rho is 1 kilogram per meter cube and R is 0.4 millimeter rise in a liquid of viscosity theta is 0.15 Newton second per meter square. Correct? And specific gravity of whom? Of the liquid. So sigma will be equal to how much? How will you convert specific gravity to density? Multiply it with 1000. Multiply it with 1000 if you want in terms of kilogram per meter cube, or multiply it with 1 if you want a gram per second. Am I clear with this point? Right? So 0.9 into 1000 is going to give you 900. So that you want me to repeat? So this is the logic. Specific gravity is given, okay? So specific gravity, if you want to convert it to density, okay? So if you want to convert it to density, I'll put it like this. Specific gravity, you can convert it to density in kilogram per meter cube or density in gram per centimeter cube. Correct? So if you want this to happen, multiply with 1000. That is the density of water at 4 degrees Celsius. Here, multiply with 1. Because the CJ's unit of density of water is, CJ's value of density of water is 1 gram per centimeter. Are you able to understand this point? So now since the coefficient of viscosity is given in terms of Newton second per meter square, and something else is also there. Density of solid is also given as 1 kilogram per meter cube. So all these things are in SI unit. So we'll multiply this with 1000. Nine point nine. Right? Then specific gravity is this. So you applied the formula, right? So first is they're asking what is the terminal velocity. I hope you can calculate it. So terminal velocity will come out as negative value because you will have 1 minus 900 in the numerator. Rho is 1, sigma is 900, 1 minus 900. So you get a negative value. Negative value indicates what? The object is rising inside liquid. The question itself they've asked. Even if it was not given, you should be in a position to answer. Right, that is the first part. Calculation, do it later, leave some space. So what is the next question they're asking? What is the terminal velocity of the same bubble in water of viscosity 1 into 10 power minus 3 Newton second per meter square? You will change the value of theta and also density. Because density of water is 1000, right? So there you will have 1 minus 1000. It's a simple problem, right? Next is a good problem. So there are 8 raindrops of radius 1 millimeter, each falling down with a terminal velocity of 5 centimeter per second. Coalesce means they get combined to form a bigger drop. Find the terminal velocity of the bigger drop. Okay. So question looks complicated, but it has something to do with conservation of volume. So what is happening? How many raindrops are there? 8 raindrops of each 1 millimeter radius are falling down with a terminal velocity of how much value? 5 centimeter per second. Right? When they get combined, what will happen? What will be the radius of the bigger drop? Will it be 8 times 1 millimeter? When will it become 8 times 1 millimeter? Had it been a linear object. This is 1. If they get combined like this, then it becomes 8 millimeter. But what is happening? Here everything is a spherical object. So when they combine to form a bigger sphere, what will happen is the volume of the liquid that participated in this combination will be equal to the volume of the bigger sphere. Right? So can I say 8 times volume of the smaller spheres will be exactly equal to the volume of the bigger sphere. Right? Because I know one thing, that if you need to find the terminal velocity, what are the parameters that you need? Recollect the formula once: 2 by 9 r square sigma minus rho into g divided by newton. So out of all these parameters, what do you think is changing? The same nature of liquid is getting combined. The same thing is falling under. So it is only the radius that is changing. So it is falling through the same medium. So density of the substance in both the cases is not changing. What about the viscosity? It's the same. Right? So can we solve the problem easily? So what I'm trying to say is, I'll solve this problem like this. I am able to understand that V is directly proportional to R square. Then I'm not going to take the other data into consideration so that there is no confusion. So I will say V dash, that is final value divided by the initial terminal velocity, is equal to R dash square. I will write it as capital R square divided by small r square. Accepted? So what is the value of V dash? That's what we need to find. V is 5 centimeter per second is equal to, what is the value of capital R? Can you guys find out and tell me? Make it fast.
Sir,
Tell me.
sir, so in this question too, like 1 millimeter on 1 millimeter on converting to centimeter should be 10 to the power minus 2, right?
Don't do it. Why are you doing conversion? Leave it in millimeter itself. Don't look at the
Okay.
solution. So this is what you wrote: 4 by 3 pi capital R cube is equal to 8 times 4 by 3 pi small r cube. Let me see. So capital R is equal to 2 times small r. I take the cube root on both the sides. So what will be the answer? 0.2. Nitish, I hope you understood. You need not do any conversion. Don't look at the solution. Okay. So
Yes.
0.2 square divided by 0.1 square. Multiply and divide with 10 inside. So 4 is to 1 is the answer. So 4 into 5 becomes 20. Did you understand what I did? So 0.2, so I'm not concerned about 0.2. What it is, 0.2 by 0.1 the whole square, multiply with 10, it becomes 2 by 1 the whole square. So 2 square is 4. So this whole thing is 4. 5 goes to the other side, 20. So 20 centimeter per second will be the new terminal velocity. This is a very good problem. I hope you understood, right? I left it in millimeter because I'm not concerned about it. If it is millimeter, this was a millimeter, it gets cancelled. And I was not concerned about it. That's what I told him also. Right? Can you guys try the next one? Last one. I want you to do it on your own. Exactly 4 minutes is there. Solve it fast. So show that if n equal rain droplets falling through air with equal steady velocity, that is called as terminal velocity, equal steady velocity of 10 centimeters per second combined, the resultant drop attains a new terminal velocity of 10 into n power 2 by 3. So for competitive exam, this will be used like a formula. Same logic. Except 8, you have 9. That's it. Can you do it fast? So what is the formula? V dash divided by V will be equal to capital R square divided by small r square. How many drops are getting combined? N drops. So 4 by 3 pi capital R cube is equal to n times 4 by 3 pi small r cube. 4 by 3 pi, 4 by 3 pi gone. R is equal to n power 1 by 3 into R. Right, take this and substitute it here. So V dash divided by V is equal to n power 2 by 3 into R square divided by R square, cancel them. So V dash will be equal to V into n power 2 by 3, but what is the value of V that is given? 1 by 3. N power, but it goes there, it becomes square, no? R square. So n power 1 by 3, the whole square is n power 2 by 3. So n power 2 by 3 to R square gone. So V dash will be equal to terminal velocity of the small drop into n power 2 by 3. But what is the terminal velocity of the small drop given? So put the 10 there. This is what they are asking. 10 into n power 2 by 3 centimeter per second. Right? I hope this is easy. So with this, we are done with the viscosity part also. So what is that we have completed? We have completed the fluid statics and fluid dynamics is also over, except Poisson's equation that I'll explain after the capillary. Okay. So the next part that we will be starting in the month of Jan is going to be surface tension. That is also a slightly tricky concept, but maximum 2 days, okay. Once we are done with it, then we'll get into thermal physics. Okay. So in the meanwhile, as I told, you will be getting assignments. First point. Secondly, the test that you have written, you will get your answer sheets by Friday morning. Okay. By Friday, you will get the marks. That's it. So I think I have not scheduled any other tests, right? So for the next week, there are no classes and you will be having assignment. So assignment based on this chapter, of which you have to work for the topics that we have completed till now. If the questions are based on surface tension or something, don't worry about it. No, I've given the schedule, right? There are no classes. So we are closed for next week and we'll meet on 3rd of Jan. In the meanwhile, if you have any doubts, you guys can reach out to me. So any doubts?
Sir, on 3rd of January, we have to come directly to the center, right? Like,
Yes.
can we come like?
It's the same procedure. It's the same thing. For Jan month,
Oh,
I'll
okay, sir.
Okay, next week I'll give you the schedule. That's it. Any other doubts? Not now. I'll start it from Jan. So I have to plan the schedule. Anything else? Clear?
Sir,
Tell me.
sir, that conversion alone, can you repeat once?
Which conversion?
Like if you take a decimal 0.3, like 0.3 millimeter to centimeter,
Nothing
so
else.
it, multiplying with 10 to the power minus 2, right?
Listen, 0.3 into milli, if you see that word, put 10 power minus 3 and meter, write it as it is. I hope this is clear, right?
Yes, sir.
Okay. So you know that 10 power minus 2 meter is 1 centimeter. You know this, right?
Yes, sir.
Centi is centum. Centum na 100 then. So 1 by 100 is what we call it as centi. Okay. So 0.3, this 10 power minus 3, can I write it as 10 power minus 1 into 10 power minus 2?
Yes, sir.
Meter. So this 10 power minus 2 meter, I'll call it as centimeter. 0.3 into 10 power minus 1. So what will happen? 0.03 centimeter. Purida.
Yes, sir. So, sir, what happens if we do directly? Like,
That depends. I never asked you to convert it to millimeter at all, to centimeter at all. I did it directly only, no? I didn't do it, see. Oh, I converted, I'm sorry. You can do it directly. See, for example, that is even more simple. R is equal to 2 into 1 millimeter. That is 2. Correct? Take 2 and substitute it there. It is even more simple. V dash divided by 5 is equal to 4 divided by 1. It's the same logic.
yes, sir.
Understood? So 4 millimeter square, 1 millimeter square. That is the meaning.
Yes,
Clear?
okay, sir.
Okay. So that's it, guys. log of. I'll see you all on third.
Thank you, sir.
Thank you, sir.